a game of cat and mouse, and you're constantly bouncing around between these possible states that you have, and based on the way that you assign variables and variable names for your control variable for the state machine will determine which state is executed, and all the lines of code that you have within that possible state will have those lines of code executed. So that's the whole purpose behind the state machine, right? So now, with the way that that this was written for this particular process, essentially what's happening is that after every command, after every state that we have that is executed, it will immediately be followed by the drop LCDE state, which is right at the very, very end, which is right here. So the state machine will go through and execute one of our possible conditions that we have. So we have display clear, we have display on, we have mode set. All of these are different conditions. However, the way that we've coded it here is that after it executes this, it will always, as sort of a default, it will jump and execute a drop LCDE before it moves on to the next state in the code sequence. It will always execute a drop LCDE state and all of the code that we have implemented there. So regardless of all of these possible states, by default, after it's done executing that particular state and the lines of code within that state, it will always go and execute a drop LCDE, because in order for that information and the signals to be sent and received successfully to the LCD, of course, you know, we need to have the LCD's enable line go to a logic low state, creating a falling edge. The fact that that's occurring, that's two cycles of the state machine. It has to go through it once and exit the state machine for the command that you're running, or the state where you're actually sending information to the data bus. So that means that our 400 hertz clock pulse, or whichever pulse that we would declare to drive the state machine, is activated once. It is pulsed high, and it drives that state once. And then what is it doing there? Well, our signal on our LCD enable is in a logic high state, and then in order to create the falling edge, it has to drive low. So it has to create another signal pulse to have the falling edge created. So from start to finish, our cycle is first high, then it's low. And so if you think about that, the period of this signal has been extended because we're using two of these pulses, because we have two states. We have the first state, which is our logic that we're sending to the LCD, and then we have to have it immediately followed by the LCD enables falling to a logic low. That's the signal cycle for the LCD enable line. If you think about it, the fact that we have that, it means that whatever variable that we've assigned to generate this pulse within our clock process, and that variable being the counter variable here, the hexadecimal number 0F424. Now, when you do the math and you process this, that particular hexadecimal value is used to generate an 800 hertz pulse. So now why was 400 hertz chosen when this variable was being used? Why is it half of what this was intended? Well, because the core was designed for us to be using two states within the state machine, one for executing the command and then one at the end for the falling edge of the enable line. A lot of you were probably couldn't understand why this clock 400 hertz enable was chosen. That's the exact reason, is because the original core that was implemented was coded to always have two states being executed one after the other before the next command would actually be run. So that's why 400 hertz, it was actually a variable here for 800 hertz, but when you actually monitored the signal with an oscilloscope on the D2's LCD enable line, it would actually come up as half the frequency, half the set frequency for this variable. Now, a lot of you are probably saying, wait a minute, I hooked up, I used the code that Jerry had put on the web page, and I hooked it up, and I hooked up my oscilloscope to the LCD's enable line, and it didn't show up as 400 hertz. It was different. It was something else. And I'll explain why. And that's because when I was manipulating things around, I added an additional state to the state machine. So we ended up having 3 states being executed, one after the other, before the next command would run. So that extended the period of that signal. And so with the period being extended, doubled, and then tripled, well, each time that's going to divide your frequency down. So that's why a lot of it. So what I ended up doing was, for the last states that I had within the state machine, you can actually move things around and shorten it so that it is in fact only 2 states. And then you will actually get the official 400 hertz as shown here. So it's a bit confusing, I realize, and I hope that I haven't lost you, but if I have, I do apologize. I'll do some samples here. We'll do some examples, pardon me, and we'll run through it. So I'm going to have this run. This is the exact way, with the added hold state that I put in there. This was exactly the way that I had it set up originally with the code that I had in the first two videos. So I'm going to compile this code, and we're going to go look at it on the D2 board, and also monitor the logic enable line on the LCD, and check out and see how that looks and how it reads on the oscilloscope. And then I'll talk about it a little more just to clarify. So let's do that now. Let's move over and program the LCD on the D2 board. Okay, so I've got the D2 board booted up with the welcome screen there. I've got the oscilloscope monitoring the LCD's enable line, and I've got Quartus here ready to load the original code that I posted on the web page. So we're going to program that now, and then we're going to check out the frequency on the enable line, and we'll investigate that. So here we go. So I'm going to program it there now. Let's watch the LCD display. So programming now. Boom, there's the message, so it works out. Now, let's take a look at the oscilloscope here for monitoring the LCD's enable line. So technically, we should have 400 hertz there. But now when you were monitoring it, you were seeing 266 hertz with a period of 3.75 milliseconds. And the duty cycle was actually 33.4. So a lot of you are probably sitting there going, what the heck is going on? This doesn't make any sense. Now the reason for this is because the period is being extended by each of the states within the LCD core, the state machine. So by running 3 states within that state machine, we're manipulating and changing the period, the duty cycle, and the frequency. What I actually ended up doing was going and rectifying this and putting it back to only actually run 2 states as it was originally designed as part of the original LCD core. So a lot of you were sitting there confused and didn't know what was going on. So the reason for this was because I had gone in and manipulated it against the original LCD core. And so by removing that hold state that I had added, by removing that, I was able to put it back to its original condition, and the frequency on the LCD enable came up to